Hello friends. In today's class we are going to talk about another classic synchronization problem called Dining Philosopher Problem. Welcome here, and we are talking about Dining Philosopher Problem, and it's a classic synchronization problem, neither because of its practical importance nor because of the computer scientists dislike philosophers. That is very funny. But because it is an example of large class of concurrency control problem. Okay, it is the example of a large class of concurrency where lots of processes are there, and there we are trying to make them synchronize. So that problem it belongs there. It's a simple representation of the need to allocate several resources among several processes in a deadlock-free and starvation-free manner. Okay? So here it is a simple representation that the need to allocate several resources among processes. Okay, several resources are there and several processes are there, and the requirement that it will be allocated. Allocate the resource. The meaning of the statement is that allocate the resource in deadlock-free and starvation-free manner. Okay. Now, philosophers spend their lives in alternatively thinking and eating. They don't interact with neighbors and occasionally pick up two chopsticks one at a time. Okay, so to eat from bowl. Sorry for that. Eat from bowl. Need both to eat. Then release both the when done. Okay, so here the meaning of this statement is whenever they want to eat, they need both the chopstick together. Okay, they need both the chopstick, and without both of them they will be not be eating. Okay, so shared data is the bowl of rice they are sharing, and like here 1 2 3 4 and 5. Main thing is your chopstick, which is a semaphore. Okay, which is a semaphore, and it is initialized to 1. This is the for structure of philosopher I, that it will wait for a chopstick I. Okay, it will down this and wait for the chopstick I, and then it will try to log this chopstick, which is I plus 1 modulo 5. Coming back here, if I say this one, suppose this is 1 2 3 4 and 5. Okay, and this is supposed to chopstick 1 2 3 4 and 5. So it needs to lock both the chopstick I1, it will lock, and it will also lock here I plus 1 modulo 5. So in this case here suppose philosopher 5 is there, so 5 will lock 5. Okay, 5 will lock this I chopstick, and it will also lock 5. So a chopstick I for philosopher I, and it will be I plus 1 modulo 5. Okay, 1. Okay, I think it is like this. Sorry. Okay, now this numbering is like this only. So this is numbered like this. Okay, this is 1. This is 1 2 3 4 5 1 1 2 2 3 3 4 4 and 5 5. Okay, so hit this one chopstick I, it will try to pick it this one, and it will also try to pick I plus 1 modulo 5. Okay, so that is the idea here. I and I plus 1 modulo 5. So here in this it will try to pick up this first fork. 2 will try to pick its first fork number 2. 3 is try to pick this 3. 4 is try to pick this 4, and 5 will try to pick this 5. Okay, and then after this it will also pick the weight. It will put a weight for this I plus 1 modulo 5, and which is equal to what? Which is equal to I plus 1 to I plus 1 modulo 5. It will also try to pick the 2. To 1 and 2 it will try to grab. 5 will try to grab 5, and it will be trying to grab 5 plus 1 modulo 5. That will try to grab 1. Okay, so that is the structure. After getting both of them, and then it will eat, then it will signal chopstick I, signal chopstick, and then it will think, and it will be keep on repeating this process. Do you see any problem with this algorithm? Okay, so yes, problem here, yes, and problem here in this case is the deadlock. Now suppose each I execute this process on chopstick I, means try to hold the chopstick. So 1 try to grab the 1, 5 try to grab the 5, right? And 4 try to grab the 4, 3 try to grab the 3, 2 try to grab the 2. Okay, if it is the case, then everyone will be, what they will do? Everyone will execute the first statement chopstick I. Right? And they all of them will, like here 1 will execute chopstick 1, 2 will execute wait chopstick 2. So this statement, and when you will come to the next statement, okay, they have already done this first one, and when you'll try to get this one, they will stuck, all of them will stuck here, and relate to deadlock. Why? For example, if 1 try to grab 1 and then it will just try to grab 2, but 2 has already put a lock into this. Okay, so this will lead into a deadlock situation. Now what can be the problem? Deadlock handling. To break the deadlock, at most 4 philosophers will be sitting simultaneously at the table, not 5, 4. Okay, what can be the another solution? Allow a philosopher to pick the fork only if both are available. Picking up must be done in a critical section. Okay, so lock both of them simultaneously, otherwise no. Use an unsymmetric solution. An odd number philosopher will pick the first left chopstick, then right chopstick, and even number philosopher will pick the right chopstick and then the left chopstick. Okay, so these are the some solution that is for Dining philosopher proposed. Okay, so this is your Dining philosopher problem, and this solution may lead into a deadlock situation. Okay, so proposed solution, again let me revise: 4 at a time, pick both in critical section, and use a asymmetric solution. Okay, so that's all for this discussion. Thank you.